In 1887, the greatest challenge facing the engineers of the Eiffel Tower was not its 300-meter height, but how people would ascend such a structure. A closer look at the tower's four legs reveals that they tilt inward at an angle of about 55 degrees. So how could an elevator be built along such a curved incline? Stairs were an option, but climbing nearly 300 meters vertically would have been exhausting. Interestingly, when the tower was first completed, many Parisians believed it ruined the city's aesthetics. The original contract even stipulated it be dismantled after 20 years. Yet 135 years later, this structure, made of 7,300 tons of steel, still stands tall. Today, when people think of Paris, the Eiffel Tower is often the first image that comes to mind. Supporting 7,300 tons on just four legs was already difficult, but the real challenge was that the tower stands beside the Seine River, where the soil conditions were extremely poor and unsuitable for foundations. This problem closely resembled the challenge faced 400 years earlier during the construction of the Taj Mahal. Matters were further complicated by the fact that the geological conditions beneath each leg differed. The northwest legs stood near the riverbank, surrounded by muddy soil and standing water, while the southeast legs rested on dry ground. To prevent uneven settling that could cause the tower to tilt, the foundations in the wet areas had to be just as strong as those in the dry zones. Let's begin with the dry ground foundations. Engineers excavated manually to a depth of 6 to 7 meters until they reached a stable layer of compact sand and gravel, which became the foundation base. They then dug multiple rectangular pits, each about 2 meters deep. This design served two purposes. First, each main leg is actually composed of 4 smaller supports, allowing the load to be evenly distributed. Second, the compact sand layer ensured stability and prevented settlement. Once the pits were prepared, they were filled with hydraulic concrete, not modern cement, but a mixture of lime, clay, broken stone, and water. This concrete had a unique property. It could harden underwater, and prolonged exposure to water actually increased its strength. After the 4 concrete bases were completed, a stone pyramid was built above them. Small stones were bonded with hydraulic mortar and stacked into a pyramid with a 54-degree slope. 2 iron anchor bolts, 6 to 7 meters long, were embedded inside to connect the upper structure. Finally, a ring of masonry was built around the 4 stone pyramids, filled with rubble and mortar to form a single platform. The dry ground foundations were complete, but the riverbank posed a far greater challenge. When excavation on the riverside reached depths of 4 to 5 meters, problems emerged. Soft, waterlogged soil turned the site into sludge, while water ground continuously flooded the pits, making work impossible. The engineers devised what was considered a brilliant solution at the time: wooden pneumatic caissons. The principle was simple. Like placing an inverted glass underwater, trapped air prevents water from entering. These wooden caissons used compressed air to block groundwater. The bottom remained open, while the top connected to access shafts through which workers entered and excavated soil was removed. The lowest working chamber was completely sealed. High-pressure air was pumped in to balance the surrounding water pressure, preventing flooding. Entry procedures were strictly controlled. Workers first entered an upper airlock, sealed the door, then increased air pressure until it matched the working chamber. Only after pressure equalization could they enter and begin excavation. As soil was removed, the heavy caisson gradually sank under its own weight until it reached depths of 28 to 30 meters, where a solid gravel layer lay. The compressed air was then released, and the caisson was filled with hydraulic concrete, forming a solid foundation. Above it, the same 54-degree stone pyramid structure was built, with anchor bolts installed to match the dry ground foundations. These structures were known as caisson piers. An arched retaining wall was built around each caisson pier. Unlike flat walls used on dry land, arches were necessary here due to uneven water pressure from saturated soil in groundwater. Flat walls could crack under uneven pressure, but arches transferred forces downward into the ground, preventing displacement and ensuring structural integrity. With stone and mortar filling, the riverbank foundations became a single, unified structure. The Taj Mahal faced similar challenges 400 years earlier, as it was built beside the Yamuna River. Engineers there used a different solution: wooden raft foundations made from special timber that hardened when exposed to water, with vertical shafts extending downward to form arched underground structures. These arches also dispersed soil and water pressure, securing the foundation, an approach remarkably similar in principle to the Eiffel Tower's arched retaining walls. Due to limited communication at the time, the engineers in these two regions developed their solutions independently. Returning to the Eiffel Tower, the foundations of its 4 legs are perfectly symmetrical, with a distance of 125 meters between each leg. Inside each caisson pier, small gaps were left around the anchor bolts. Above them, base shoes were installed, critical components that connect the tower's steel structure to its concrete foundations. Assembly of the tower then began. All components were prefabricated in factories and assembled on site, totaling more than 18,000 individual steel parts. These parts were not welded, but joined with hot rivets. Heated to 800 to 900 degrees Celsius, rivets were inserted into holes and hammered into place. As they cooled, they expanded, locking the components together. Around 2 million rivets were used. Remarkably, the steel contained 99% pure iron with just 0.02% carbon, and slag fibers within the metal greatly slowed corrosion. When the four legs reached a height of 57 meters, they needed to be joined by a platform. Even with precise fabrication, slight dimensional differences remained, making alignment extremely challenging. Engineers had anticipated this. The small gaps around the anchor bolts allowed for minor adjustments. The real challenge was moving the 1,500-ton legs, as cranes of the time were inadequate. Wooden support towers were built, and hydraulic jacks were installed within each foundation pit. Using manual controls, engineers adjusted the legs with micrometer-level precision. Once aligned, temporary wooden scaffolding was erected beneath the platform, and cross-bracing and horizontal tie frames were installed to stabilize the structure. The platform was then completed, and decorative arches were added between the legs to enhance the tower's appearance. Today, the first level of the Eiffel Tower is a vast space that even includes restaurants. During construction, workers relied on wooden scaffolding. As the tower rose, transporting materials became increasingly difficult, relying mainly on steam engines and manual chain hoists. After the first level was finished, work began on the second level, assembled with the same precision at a height of 150 meters. Beyond the second level, construction entered the final phase, the tower's summit. Up to this point, the four legs rose independently. From the second level upward, they gradually converged into a central shaft to reduce wind-induced twisting forces and better distribute weight. When completed in 1889, the tower stood 300 meters tall. Today, with broadcasting antennas, its height reaches 330 meters. Gustave Eiffel even reserved an office for himself at the top. But how could one reach it? The answer was a specially designed elevator. Modern elevators use vertical shafts and counterweights, but the Eiffel Tower's 54-degree inclined legs made this impossible, requiring curved elevators instead. Otis engineers developed this system by installing curved rails inside the legs. Elevator cars moved along them on wheels, much like trains. Power came from a hydraulic system with a 16-meter piston. The piston didn't move the car directly, but transmitted force through multiple pulley systems. For every meter the piston moved, the car traveled 8 meters, an amplification achieved through pulleys. These pulleys ran through the tower to the second level, where cables connected to the elevator car. When the piston pushed, the car rose. When it retracted, the car descended. Hydraulic accumulators stabilized pressure, stored energy, ensured smooth operation, and acted as backup power in case of system failure. All four legs were equipped with such curved elevators, some for visitors and others reserved for staff and restaurant service. These elevators only reached the second level. From there to the summit, a more conventional electric elevator system was used. 4 elevator cars operated in pairs, 2 ascending while 2 remained on standby, functioning as counterweights. As one car ascended and another descended, 40 to 50% of the load was offset, significantly reducing motor strain. Once criticized for spoiling Paris's beauty, the Eiffel Tower overcame challenges of foundations, assembly, and access through engineering ingenuity, becoming a miracle of world engineering.
For 135 years, it has witnessed Paris's transformation and stands as a testament to the intelligence and power of the 19th century industrial age. Thank you for watching. See you in the next video.